Today, we delve into the critical aspects of hydrogen electrolysis, focusing on its thermodynamic foundations and the practical efficiencies achieved in real-world systems. Our objective is to gain a comprehensive understanding of the inherent energy minimums and the various efficiency trade-offs that govern this pivotal technology. As engineers, researchers, and scientists, it's imperative to grasp these fundamental principles to optimize system design, improve operational performance, and ultimately drive down the cost of green hydrogen production. We will analyze the energy requirements from a first principles perspective, moving through theoretical limits to the complexities of practical implementation. This analytical journey will equip us with the insights needed to address the challenges and opportunities. Over the course of this presentation, we will systematically explore several key areas to build a robust understanding of hydrogen electrolysis. We'll begin by examining the fundamental reaction and its thermodynamic floor, establishing the absolute minimum energy required. Following this, we will break down the energy components, specifically the Gibbs free energy and enthalpy, to understand their roles. We will then translate these theoretical values into practical units of kilowatt-hours per kilogram of hydrogen. Our discussion will progress to real-world energy consumption and efficiency, contrasting ideal scenarios with operational realities. We'll analyze the polarization curve, a crucial diagnostic tool, and investigate the relationship between efficiency and current density. Finally, we will consider the co-production of oxygen and conclude with a summary of our findings. At the heart of hydrogen electrolysis lies the fundamental chemical reaction, the splitting of a water molecule, H2O, into hydrogen gas, H2, and oxygen gas, O2. Specifically, this reaction is represented as H2OL, H2 plus 1 to 2 O2G. For every molecule of hydrogen produced, 2 electrons are transferred, signifying an electrochemical process. From a thermodynamic standpoint, we define 2 critical voltage thresholds. The reversible voltage, often denoted as EREV, is 1.23 volts. This represents the absolute minimum electrical potential required to drive the reaction under ideal reversible conditions, corresponding to the Gibbs free energy change. However, considering the enthalpy change, which accounts for both electrical work and heat, we arrive at the thermoneutral voltage, ETIN, which is 1.48 volts. This higher voltage signifies the energy input needed if the process were to be entirely self-sustaining without external heat exchange. Based on these principles, the absolute minimum energy required to produce 1 kilogram of hydrogen is precisely 32.68 kilowatt-hours. To fully appreciate the energy requirements for water splitting, it's essential to dissect the total energy into its constituent thermodynamic components. The overall energy change for the reaction, represented by the enthalpy change, dH, is the sum of 2 primary terms: the Gibbs free energy change, dG, and the entropic contribution, TDS. The Gibbs free energy, dG, quantifies the maximum reversible electrical work that can be extracted from or supplied to a system at constant temperature and pressure. In the context of electrolysis, dG represents the minimum electrical energy input required to drive the reaction. The TDS term, where T is the absolute temperature and ds is the entropy change, accounts for the heat energy exchanged with the surroundings. For water splitting, dG is approximately 237 kilojoules per mole, while TDS is about 48.6 kilojoules per mole. Therefore, the total enthalpy change, dH, which is the sum of these two, represents the total energy required, encompassing both the electrical work and any necessary heat input or removal. Translating thermodynamic values from a molar basis to a mass basis is crucial for practical engineering applications. Our goal is to convert the energy requirement from kilojoules per mole to the more industrially relevant unit of kilowatt-hours per kilogram of hydrogen. We begin with the Gibbs free energy change, which is 237.2 kilojoules per mole of hydrogen. To convert this to a per kilogram basis, we first need to determine how many moles of hydrogen are in 1 kilogram. Given that the molar mass of hydrogen, H2, is approximately 2.016 grams per mole, 1 kilogram of hydrogen contains 1,000 grams divided by 2.016 grams per mole, which equates to approximately 496 moles per kilogram. Multiplying 237.2 kilojoules per mole by 496 moles per kilogram yields 117,651 kilojoules per kilogram. Finally, to convert kilojoules to kilowatt hours, we use the conversion factor that 1 kilowatt hour equals 3,600 kilojoules. Dividing 117,651 kilojoules per kilogram by 3,600 kilojoules per kilowatt hour gives us the absolute minimum electrical energy requirement of 32.68 kilowatt hours per kilogram of hydrogen. While thermodynamics establishes a theoretical minimum of 32.68 kilowatt hours per kilogram, practical electrolysis systems invariably consume more energy due to various irreversibilities. In real-world operations, the energy consumption for the electrolyzer stack itself, operating on direct current, typically ranges from 40 to 50 kilowatt hours per kilogram. When considering the entire system, including power electronics, pumps, compressors, and other auxiliary components, the total energy consumption for a typical electrolysis plant can range from 50 to 65 kilowatt hours per kilogram of hydrogen produced. This translates to a practical system efficiency based on the lower heating value of hydrogen, generally falling between 55% and 70%. For instance, current Department of Energy targets and specifications from leading manufacturers like Cummins often indicate consumption figures in the mid-50s kilowatt hours per kilogram. This significant difference from the thermodynamic minimum highlights the engineering challenges in minimizing overpotentials and parasitic losses across the entire system. The polarization curve is an indispensable tool for characterizing the performance of an electrolyzer cell. It plots the cell voltage against the current density, providing critical insights into the various overpotentials that contribute to energy losses. At low current densities, the voltage is primarily influenced by activation overpotentials, which are associated with the kinetics of the electrochemical reactions at the electrode surfaces. As the current density increases, ohmic losses become more significant. These losses arise from the electrical resistance of the electrolyte, electrodes, and interconnects within the cell. At very high current densities, mass transport limitations begin to dominate. This occurs when the rate of reactant supply to the electrode surface or product removal from it becomes insufficient, leading to a further increase in voltage. Understanding these contributions is vital for optimizing electrode materials, cell design, and operating conditions to minimize energy consumption and maximize efficiency. A critical trade-off in electrolyzer operation exists between system efficiency and current density. As the current density increases, the cell voltage also rises due to the combined effects of activation, ohmic, and mass transport overpotentials. This increase in voltage directly translates to a higher electrical energy input per unit of hydrogen produced, consequently leading to a decrease in overall system efficiency. For example, while an electrolyzer might achieve 80% efficiency at a low current density, pushing the system to higher current densities, perhaps to maximize hydrogen throughput from a given footprint, could see efficiency drop to 60% or even lower. This inverse relationship means that operators must carefully balance the desire for higher production rates, which reduces the capital expenditure per unit of hydrogen against the increased operational expenditure due to lower energy efficiency. Optimizing this balance is a key engineering challenge, often dictating the economic viability of a hydrogen production facility. An often overlooked aspect of hydrogen electrolysis is the stoichiometric co-production of oxygen. For every kilogram of hydrogen produced, approximately 8 kilograms of oxygen are simultaneously generated. This is a direct consequence of the water-splitting reaction, where one molecule of water yields one molecule of hydrogen and half a molecule of oxygen. Furthermore, the process consumes a significant amount of demineralized water. Specifically, about 8.92 liters of water are required to produce 1 kilogram of hydrogen. The co-produced oxygen, while often vented, represents a potential additional value stream. In industrial settings, high-purity oxygen can be utilized in various applications, such as medical uses, steel production, wastewater treatment, or chemical synthesis. For instance, a facility producing 364 kilograms per hour of hydrogen would concurrently generate approximately 2.9 metric tons per hour of oxygen. Recognizing and monetizing this oxygen byproduct can significantly improve the overall economics of green hydrogen production. In summary, our analysis reveals several critical insights into hydrogen electrolysis. Firstly, thermodynamics establishes an immutable energy floor of 32.68 kilowatt-hours per kilogram of hydrogen, representing the absolute minimum electrical energy required. Secondly, practical electrolysis systems invariably consume more, typically ranging from 50 to 65 kilowatt-hours per kilogram, due to inherent irreversibilities and auxiliary power demands. Thirdly, a fundamental trade-off exists between efficiency and current density. Higher current densities, while increasing throughput and potentially reducing capital expenditure, lead to decreased energy efficiency. This necessitates careful optimization to balance operational and capital costs. Finally, the co-production of oxygen, at a ratio of 8 kilograms per kilogram of hydrogen, offers a valuable potential revenue stream that should be considered in economic assessments. Ultimately, no technology can circumvent the fundamental energy barrier imposed by thermodynamics. Our engineering efforts are focused on closing the gap between theoretical ideals and practical realities.